Hello, this is Tejaswini Sumanam. Today I am going to talk about Spintronics. These are the topics I am going to discuss in today's presentation. Let us try to understand what is Spintronics. Spintronics means spin transport electronics. It is also known as spin electronics or fluxtronics. It is the study of intrinsic spin of the electron and its associated magnetic momentum in addition to its fundamental electronic charge in solid-state devices. Directional and coherent motion of electron spin circulates a spin current which will carry or transport information and control quantum spin in a spintronic devices. Let's begin with the question, what is special about electron spin? From a scientific and technological point of view, there are four important points. First is the connection between spin and magnetism, which is useful for information storage. Second is an intrinsic connection between spin and quantum mechanics, which may be useful for quantum information. Third is the short range of spin-dependent exchange interaction, which implies that the role of spin will continue to grow as the size of nanostructure continues to shrink. Fourth are the issues of speed and power dissipation, which are becoming increasingly important for electronics at the nanoscale. Spintronic differs from the older magnetoelectronics in that the spin are not only manipulated by magnetic fields but also by electric fields. Spintronic is the combination of best of two different worlds, ferromagnetics and semiconductors. Ferromagnetics has stable memory, fast switching, high ordering temperatures, whereas semiconductors have band gap energy, carrier density, electrical gating, long spin lifetime. Magnetoresistance is the change of resistance of a conductor in an external magnetic field. In a typical metal, at room temperature, orbital magnetoresistance effects are very small, at most of the order of a few percent. It was not possible to significantly improve on the performance of magnetic sensors based on magnetoresistance. In 1988, two research groups independently discovered materials showing a very large magnetoresistance, now known as giant magnetoresistance. Giant magnetoresistance, a nanoscale phenomena. Giant refers to huge change in resistance due to current. It is a quantum mechanical magnetoresistance effect observed in a thin film structure composed of alternating ferromagnetic and non-magnetic conductive layer. Here is a figure representing the phenomenon of GMR. When the magnetization of two outside layers is aligned, the resistance is at its lowest. Conversely, when the magnetization vectors are antiparallel, a high resistance is developed. As we know, small fields can produce big effects. Parallel and perpendicular fields are developed depending on the spin. These are the applications of GMR, a spin valve sensors used in ABS and ESP systems of car. Hard disk drives. Hard disk drives are used in personal computer. It is a mechanism that controls the data storage for personal computer. MRAM. GMR multi-layer structures are also used in magnetoresistive random access memory as a cells that storage one bit of information. The main application of GMR is magnetic field sensor, which are used to read data in hard disk drives, biosensors, microelectromechanical systems, and other devices. Quantum computers. A quantum computer maintains a sequence of qubits. A single qubit can represent a 1 or a 0 or any quantum superposition of those two qubit states. Spin transistor. Magnetically sensitive transistors are spin transistors. Here is an application for spintronics. Simplest but most useful spintronic device is the spin valve. It is used in hard disk drive to read information in the form of small magnetic fields above the disk surface. Spin valve works on a principle called as injection and detection of spin. Sample of gallium arsenide or aluminum gallium arsenide quantum well heterostructure with an magnetic or non-magnetic metallic layer acts as spin injector electrode. It works in a reverse bias so that electrons are injected from the metallic layer into the heterostructure. The graph represents the degree of circular polarization measured against the wavelength. The red stars from the magnetic sample, whereas blue stars are the non-magnetic samples. The feature in the magnetic data thus have a clear magnetic origin and they demonstrate spin injection into gallium arsenide even if the efficiency is low. Although this has a payoff with a greater spin relaxation rate, we use quantum well as a spin detector to enhance the radiator recombination efficiency. The major aim of spintronic application is to improve the spin detection efficiency. It can be done by increasing the photoexcited electron spin polarization using highly spin FM electrode. New ingredient of Spintronics is CIT, current induced torque, also known as spin transfer torque. It is a key element for next generation magnetoresistive random access memory, logic in memory architecture and high density memory devices. MRAM is one of the first spintronic devices that have been invented. Unlike conventional random access memory, these do not lose data once turned off. MRAM promises density of DRAM, speed of SRAM, non-volatile like flash. Unlike conventional RAM chip technologies, data in MRAM is not stored as electric charge or current flows by magnetic storage elements. The elements are formed from two ferromagnetic plates, each of which can hold a magnetization separated by a thin insulating layer. One of the two plates is a permanent magnet set to a particular polarity. The other plate's magnetization can be changed to match that of an external field to store memory. This configuration is known as spin valve and is the simplest structure for MRAM bit. A memory device is built from a grid of such cells. Tunnel junctions are used to read the information stored in MRAM, typically 0 for 0-point magnetization state and 1 for anti-parallel state. Here is a figure which shows the array structure of MRAM. For reading from the MRAM, transistors of the selected bit cell is turned on and current is applied in the bit. For writing in the MRAM, transistors of the selected bit cell is turned off and current is applied in the bit and word line. Here is a tabular column which shows how MRAM is best when compared to all other memory devices. A quantum computer, in contrast, lies on an encoding information within the quantum bits or qubits, each of which can exist in a superposition of 1 and 0. Quantum computers could be immensely faster than any existing computer at certain problems. That's because qubits work together can use the quirks of the quantum mechanics to quickly discard the incorrect paths to a solution. However, qubits are tricky to operate because quantum states are so delicate. Another application of GMR is spin transistors. Magnetically sensitive transistors are spin transistors. Current passed through a magnetic field becomes spin polarized. Ideal use of MRAM would utilize control of the spin channels of the current. Spin transistors would allow control of spin current in the same manner that conventional transistors can switch charge current. Using array of these spin transistors, MRAM will combine storage detection, logic and communication capabilities on a single chip. This will remove the distinction between working memory and storage, combining functionality of many devices into one. Here is a figure of Datta spin transistors. It is the first spin device proposed for metal oxide geometry in 1989. Emitter and collector are ferromagnetic with parallel magnetizations. The gate provides magnetic field. Current is modulated by the degree of precision in the electron spin. Here are some of the advantages of Spintronics. It has low power consumption, low power dissipation, more compact as it takes lesser space on chip, spin manipulation is faster, it does not require unique and specialized semiconductors, it uses common metals such as aluminium, etc. Here are the recent trends of Spintronics. Spin properties of electrons are yet to be mastered. It holds vast opportunities for physics, device engineering, and material and technology. Potential of field is colossal and continuous development is required. Here are some of the references I have used in presenting my topic. Thank you.